A very good morning and warm welcome to the third day of the webinar WCISP 2022, organized by the Department of Electronics and Communication Engineering and Electronics and Instrumentation Engineering, Silicon Institute of Technology, Bhubaneswar. During the last 2 days of the webinar, we had wonderful sessions and have gathered knowledge from our eminent speakers from various corners of India and abroad. Today's sessions are going to be even more interesting and informative with our esteemed experts. Now, to begin with, I take the privilege to introduce you all our first speaker of today's session, who was one of our favorite colleagues before a few years and an alumni of Silicon, Dr. Bhubaneswar. Dr. Biswal is currently serving as an assistant professor, Department of Computer Science, New Mexico State University, USA. Dr. Biswal was a faculty of Silicon from 2009 to 2014. He holds a PhD in electrical machine learning, computational modeling, auditory biophysics, smart grid, and autonomous driving. A hearty welcome to you, sir, from all of us. Sir, I would like to invite you to
So it's going to be more like a review. I'm not going to talk on a specific thing and go in depth into it. But the entire goal of this particular talk is going to be completely kind of introducing you to some of the stuff which all of us know. So it's primarily aimed at students and early stage researchers who have been searching for some sort of problem to work with, or you know, it's kind of a status update. And then briefly, I'm going to talk about certain machine learning and signal processing aspects and how do both of these stuffs combine. So my talk is going to start with certain historical notes. Like, before a few years, I was some recent updates. So it's going to start with so I have around an hour. This is the okay, cool. Sorry about the mess up right now. Cool. So to start with, when we talk about signal processing, that basically the thing that basically comes to our mind is particularly the LTI system, linear time trading system. And then we talk about mostly filtering and then spectrum analysis. So, and lastly, information retrieval. So these are the four aspects that often comes to our mind when we talk about signal processing. And when we talk about machine learning in a classical context, it's more like a classification problem where we basically try to classify different patterns or like model systems through regression or techniques like clustering or more often again the other part would be reinforcement learning. We primarily focus on so, so here is a classical okay. Yeah. So always started with we always started with some sort of input, and that we extracted like the major focus for signal processing was to extract meaningful feature out of it, and then once the features are extracted, the other thing was to take a data driven model or a machine learning model that will basically take some sort of decision based on the features that were extracted. So it could be the data driven model, could be a regression model where we try to kind of like model the whole system, be it a inverse modeling task or something, or mostly in this context it would be a classification problem mostly. So some sort of neural network or some sort of other kind of machine learning algorithm that would take on these features as input, and then kind of what is the intelligent decision. So when we look at the classical context of like machine learning systems and like feature extraction, if we talk about feature extraction, it's primarily reducing the dimension, or to like the goal of feature extraction was to retrieve some sort of key information that we could use for either like do some sort of discriminant analysis, or to kind of uniquely uh, classify or kind of cluster or whatever. So then we like as we talk about feature extraction, we talk about like we used to use principal component analysis, finding out these eigenvalues or eigenvectors, or there were like we could use compressive sensing where we have a reduced dimension representation of a higher dimension input, which could be an image or a speech signal or whatever it would be. And or we could go for spectral analysis. Again, that's when we talk about spectral analysis, we want to go for it like a domain-wide mapping. And when we do a domain-to-domain mapping, sometimes we kind of extract some sort of key spectral features that could be useful. Then something like wavelets or multi-resolution analysis or time frequency analysis were kind of key elements there in order to do any kind of classification, like like any kind of feature extraction per se. So if we have a look at the classical machine learning algorithms, like classical context of machine learning, we had supervised learning, of course, semi-supervised one, mainly supervised and unsupervised, where we had some supervised data to train for, and then in unsupervised we had all this clusterings, and semi-supervised one where we had a part of supervised as well as unsupervised. So all these things are kind of classical approaches. If you look at it again, so far as like one of the key concept was optimal linear classifier. So where it could be simply finding out the linear hyperplane that could basically distinguish between in this case 2 classes, because I'm basically taking an example of vector machines. But again, it can be a multi-class classification. So where we could have multiple hyperplanes that could separate all this input data based on their features. Different classes. So I think support vector machines, all of us know. I don't want to get into the details of it, but the whole approach was to classify different kind of data based on the features that we get. And the essential optimization problem here is to kind of like find a linear decision boundary, and then based on the data, or like based on the feature points, the goal was to find out the maximum margin around that classification boundary. So essentially what we want to do here is to find this classification boundary by minimizing the overall end-to distances, so that we kind of like by changing the slope of it, and shifting the bias, we wanted to find out the optimal decision. And that was something which basically did really good stuff and a lot of business papers and a lot of. Then we had nonlinear classifiers per se. So where instead of having linear decision boundaries, we could go for nonlinear decision boundaries. So it's not just essentially hyperplanes and so kind of like on the feature space, even if the boundaries are nonlinear, we could model them with typically multi-layer persistence or multi-layer neural networks. So when we talk about these multi-layer neural networks, what they used to do is to again features that we extract. These features were again mapped onto a higher dimensional sphere based on the hidden layers, and that way on the hidden layer itself, on the overestimated feature set, we used to have linear decision boundaries together. But again, it's a non-linear classifier, so on the feature space, the decision boundaries are non-linear, and essentially through the process of trading, we used to do things. Now I want to focus on certain works which I started on my early days, somewhere around 2013. I started working on this particular problem while I was working on a smart grid center for improving the control and protection of electricity grids. And there, I'm going to talk about where we started and how the modern, machine learning techniques took over. So, Option. This one, right? Sorry about the interruption. So now, here the goal was that, so typically for, particularly for the electricity grid, we have a control systems center. The control center basically, essentially, it's kind of currently we have this SCADA data which will have these remote sensors. They will basically be measuring the voltage and current phases as well as some frequency values, and based on that, we could take some sort of control actions on the server, on the control center. Not going to go into details of it. But, so here was the problem. Here is the problem that I worked on at the initial stage. Here the goal was that the stars that you basically see are typically the phasor measurement units. This EMUs or phasor measurement units are nothing but they are kind of a sensor model. You could basically perceive them as sensor models that perceive the current and voltage waveforms, and then typically they record the phasors. It's like there is a a CT and a PT, a potential transformer as well as a current transformer are there. So they basically sense this high voltage data and then convert them onto these types of just digital measurements. And these measurements are often put in terms of magnitude, phase, and we also have derived quantities like frequency and rate of change of phase, this kind of stuff. So this PMUs are sparsely spaced, placed across the grid. So now in India, we have around, so maybe if I'm not correct, I'm not sure, but it's around 3,000 or 4,000 PMUs throughout the country. But in the US, when I started this work at that point of time, there were only 299 PMUs. No, because it was around 300%. So 300 PMUs on the entire Western Interconnect. So we call it as WCC, Western Electric Coordination Council. So that basically covers half of the United States. Right now, we have around 4,000 PMUs, 4,000 to 5,000. So the whole idea was that on the control center, once we have all this PMU data, can we basically do some sort of so essentially, the PMU data in the classical context were used just for the post-mortem analysis. That means if there would be any kind of failures or any kind of disturbances on the electrical system, so we wanted to know the root cause of those problems by analyzing those behaviors. And mostly this data analysis was done offline, and the typical purpose was to go for a post-mortem analysis or to find out root cause. So in this work, the whole idea is that if we have all these streams of PMU data, and if we take those data, then can we have a situational awareness? Can we have a status of the grid real-time visible, and then can we identify different kind of disturbances that occurs in the grid? So that was that was the goal. So the whole group. So right now, in order to protect the power system, we have all these relay networks. Now the relay networks are they are based on the local settings and local coordination among all these relays. But this on the PMU front, what we wanted to do was to have a supervisory layer, which will basically get this PMU data, and somehow or other, if there will be some sort of relay failure and a cascaded failure occurs, which could lead to blackouts and all, can we basically get rid of those? So now what I did was a very, very simplistic approach. The idea is that take all these time domain waveforms, convert them onto a time frequency domain representation. Essentially, what it means is we are doing simple spectral analysis and see if this spectral signatures in certain way, if we can extract some sort of features out of it, can we basically identify these all different kind of disturbances that are present, and can we automate the whole process? That was the goal. So the essential task was to put a put a module on the control center that basically gets all the feedings from the PMUs and classify all the disturbances. So now what I did was, so now when we talk about features, how do we identify kind of features that would be uniquely described in any single type of disturbances or something? So if you look at all these time domain waveforms for the voltages or the currents, they basically look to us kind of so we cannot directly correlate some sort of physics with the disturbances that we observe or the signatures that we observe. So one of the approach was that can we identify some sort of statistical features out of it, and these statistical features from the time frequency spectrum, and can we take those statistical features and do some sort of can uniquely identify the feature. Stationary frequency so stationary frequency, right?
Yes, sir.
Okay. So stationary frequency is basically a derivative of the phase, right? Del phi. Okay. So this one, what I did was a time frequency, transformation based approach. So essentially, this is basically Stockwell transformation. So it's kind of STFT. But what happens in STFT is short time Fourier transformation is like you have a window, you have a Hanning window or some sort of, or maybe a rectangular window also, like it could have. But you take a window and then over the window of that particular signal, you basically calculate the effect, right? And then this window keeps on shifting and you keep on calculating it. But what happens in that way is, so we always have a constant frequency resolution. So we don't have, so if the resolution keeps on changing, so we need to, so there is a trade-off between the time resolution and the frequency resolution. So if we keep this window length constant all the time, so what we essentially lose on is, so we are not making a compromise between the time and frequency resolution. So it's kind of a stationary. Yeah, I took a variable window so that what would happen is if the window shapes are smaller, then it would be particularly it will have a better time domain localization. It could basically say that when we are finding out the instantaneous frequency, so frequency at a particular point, we can calculate frequency at a particular point, right? We have a particular value. So we essentially have to take a small window around it. So now when we talk about that small window around it, how small it should be. So if you make it too small, think about if the frequency is, a lower frequency is present, with a small window, we'll have only a part of it. And we won't be able to, extract that frequency out of it. If we take a larger, so for the smaller frequencies, we need a larger window. But when we take a larger window, we are compromising again on the time.
resolution. So it's kind of a chicken and egg problem. So we call it as like inspired by the Heisenberg's uncertainty principle. We call it as Gabor uncertainty principle. So in this Stockner transform-based approach, it's kind of so we make a trade-off. So it's a redundant transformation per se. So it's not one-to-one. It's basically a lot of. So you will see that like in case of FFT for the endpoint signal, we'll have an endpoint. But in this case, it's basically n squared. It becomes endpoints on the frequency front and endpoint on the time front. So what we essentially do is we keep on varying this. So that's why it's a part of multi-resolution analysis. So we vary the resolution based on the window length. And then we have the basis frequency, the basis functions, which are the frequency functions, sinusoidal or cosinusoidal. They keep on varying on their entire range for this particular thing. So it's kind of a like STFT overtly done STFT. So yeah. So when we talk about the window, that plays a significant role here. So now the literature, the basic literature basically says us that like we need to take any window that would have some sort of tapering in order to reduce the ringing effect. But when we talk about reducing the ringing effect, what's the filter that would give us, or what's the window, what type of window would give us the minimum amount of ringing? That would be one thing that would come into our mind. But again, so when we talk about reducing the of the time resolution, because it again gets there. So in my case, I just took the Gaussian window, but again, like what I did was I basically modified some of these Gaussian window parameters. So you will have essentially the standard deviation in the mean, but in addition to the standard deviation in the mean, I basically did some extra parameterization to have a optimized window, optimal shape of the window that could basically extract the frequencies present at a particular particular time. So it's kind of an optimization approach. It's the similarity is up to like you can find similarity with matching percentage. So the shape of the question. So one of the things is spectral energy. Right? What you could basically do is this TFRs that you see, the time frequency differentiation. Essentially, what you want from this time frequency resolution is that if there is let's suppose if you take a signal which is constant like that, and there is one sinusoid there. So if I take the time frequency representation, I should basically find out the representation of that particular sine wave as a constant line somewhere. It goes on zero and a small constant line somewhere. So what I did was, now if we know what we want to do, so what we could essentially do is we can have a recursive algorithm which keeps on optimizing this window shape in order to find this line to be as thin as possible and as prominent as possible. So so just to give you an example, so if you see here, you can see this line here, right? So this blue line, right? Or maybe if you check out here the red one, right? If you look at this red point, that basically is flared up because of the ringing effect or because of the leakage. So if I try to optimize my window in certain way so that it becomes thinner and thinner, that way what I'm actually doing is I'm concentrating most of my energy around the frequency that is present, and I'm basically getting rid of all the ringing effect or all the leakages that are present. So the optimization criteria. So I can take it offline and basically explain you how to do that. But the simplest approach would be to run optimization to make the spectral energy, the energy concentration, edge concentrated as possible or edge compact as possible. That's so. That's again. So again, you can use it for speech and other kind of like any kind of signal processing. So just to extract different kind of right kind of spectral features, typically on a temporary domain. That's what. I can talk more about it. So yeah, so when we went ahead with all these classical approaches, one of the key thing is, just to find out like what features are critical. Now, if it is a physics-inspired design, then probably we could know that okay, these are all the features that would be important. But if it is not a physics-inspired design, like like I showed beforehand, we have all these time domain temporal reforms, but we can't really say that based on certain characteristics that these are all the features. If we extract them well, then they can distribute between this bunch of reform versus the other bunch of reform. Then the other thing is that what's the best number of features to do? So if you have too many number of features, that's not good. And if you have too few features, that's also not good, because you might have a lot of redundancy, or you might have too much of sparseness, such that you can't basically distribution. Then the other thing is that on the classical context, if we have time variant systems, so where the impulse response of the system keeps on varying, system response like we were seeing seeing those in terms of signals. But again, the signals that were generated by the system, if the system response itself keeps on varying with respect to time, then that's again becomes a harder problem to solve. Then yeah. Okay. And then the last problem would be, how do we design a particular classifier? Which classifier is going to be the best one for my solution? So in the classical context, all these things were dependent mostly on the designer's knowledge. So tacit experience used to play a role, and more often you used to do a lot of analysis to find out which classifier would be good and which set of features would be good. Now, the other thing is that the process of feature extraction, typically the signal processing engineers, their major focus was to design right kind of features. So, but now signal processing has a inherent shortcomings, I would say, that we often concentrate on the linear models, then Gaussian statistics and stationary dimensions. But essentially, the world is not stationary, non-Gaussian, and non-linear. So we have approximation techniques in signal processing to take care of those. But can we go ahead with an approach in which we could basically go for an approach where we can integrate both the feature extraction as well as the classification stage or the machine learning stage together? And that's where the modern day machine learning comes into picture. So I would say that support vector, won't go detail onto it. I think we all know from the textbooks that it all started with the Maclaurin-Fitts model, the simple neural model, and then it evolved onto finally the key indicators were solving the Adeline Exxon problem, then MLPs, and the major game changer was support vector machines. So vector machines, when first introduced by Wapnick, I think it's an AT&T Bell Laboratories, they essentially tried to identify the addresses, all those like numbers, like zip codes, automatically scanning all those images and then doing this digit recognition. And support vector machines did an exceptional job there. And then we have deep neural networks. So where we basically get rid of this feature extraction and we do an automated feature extraction. So now if we look at the typical stuff that we do in the modern day deep learning era, is that the feature extraction itself is taken care in the process of training, or maybe like what I would say is that instead of a subject matter expert deciding on what feature to use and what are the optimal set of features and what features would what should be the filter we should use, or anything of that sort, like maybe the lower dimensional mapping, all these things. If we don't want to do any of those things, and if we want to use a simple neural network that basically does the feature extraction for us and then does the classification for us. So that gave rise to something called as a convolutional neural network. Now the convolutional neural networks were there right from I think from 1980s we had convolutional neural networks. In 1978 paper, I think they proposed that. But the problem was that It's like, essentially each of these convolution layers are essentially a filter. This is one filter, this is another filter. And what we are essentially doing is we are optimizing the parameters of these filters in certain ways so that optimal features are extracted. And these features are again fed onto this fully connected layer. The fully connected layer is nothing but a neural network that basically takes all these features onto onto account and does the classification. The only difference is that, so what we have done is we have combined this feature extraction as well as the classification layer, the neural network layers together. And then we are taking care of all these parameters through a optimizing function or through a loss function. So essentially, so I don't want to get into this. This is very simple, like very basic image processing. So we had all these filters, predefined filters. Now instead of having predefined filtered coefficients, we are the deep neural network basically tries to find out the features itself or the coefficient itself. So now we have, so it's just an example of BGT16. I don't want to get in depth into it, but the simple ideology is that we have multiple stages of extracting these features. So it's kind of essentially from this stage to this stage. It's basically this stage until this stage. These are all stage by stage multi-resolution analysis. Essentially, we are doing multi-resolution analysis on the first few stages, and then we have the fully connected layers that basically does the classification. So now, going back to the problem that I was discussing, so this basically, I've taken a real world example that it's the Las Vegas area in Nevada. So these are all the actual PMU locations that we had, and there is a PDC here. So PDC basically is like it stands for Phasor Data Concentrator. So what this PDC does is that it collects all this data from all these PMUs, the real-time data. They basically communicate all this real-time data to the PDC. And the PDC essentially, in classical context, it's just used to store all the data, do nothing. And if there would be any kind of regulatory violations and all, you can basically get all this data from the PDC. So there is also another concept called as a super PDC. All these PDCs basically communicate all the data to the whole countrywide, data repository kind of thing. They call it a super PDC. But again, essentially, it just does archiving. So what we did here was that on the PDC, we thought, why not keep the supervisory control layer right at the PDC? And all these measurements that we collect from each of all these PMUs, basically all these things goes onto the PDC, and there we could do the classification approach that we wanted to do. So what I did here was, instead of going into the kind of intuitive feature finding out, then zeroing on what smaller set of features that you want to take and all these things, what I thought of is that if we have a lot of data available, why not go for a simple data-driven approach? Try to find out features, try to find out automated features. So I'm not going to tell anything to the model about which features would be important or whatever would work. So can we just do that? And in order to do that, what I did, so these are all time series. So, and then the essential part of this PMU data is, these are basically multi-dimensional time series. That means that in a particular geographical area, if you have 15 or 20 PMUs, you could have all these 15 or 24 channels of all these data. So what I did was, I combined all those data to create an image. So this is not a time frequency representation. What I did was, it's a pseudo-color image, keeping all these multi-dimensional voltage and current waveforms. So you'll see this boundary here, because this is basically one part is voltage. So I basically took voltage and frequency. So one part is voltage and another part is frequency, and then putting all this multi-dimensional data in terms of a image. So now, once we have this particular image, can I basically feed it onto a simple convolutional neural network that could extract automatic features out of it? Can basically, essentially, if you look at it, it's kind of tries to find out which all variations. These are all temporal variations per se. We don't have any spectral information here, but can we just use those temporal variations in certain way to distinguish between different kinds of classes? So I took a very simplistic approach. So took a simple, like it's a Linux type convolutional neural network. As you can see, it's not even deep. So you'll see that, these input images, I basically put them onto a convolutional layer with just a 5 by 5 kernel, and then had a max pooling layer afterwards. I'm not going in depth onto that, like why do we need max pooling and all those things, but so it's essentially for regularization. Then there was a flattening layer, and then a fully connected layer that basically does the classification. So the interesting thing here is that it worked. This kind of model worked really well. So it's a data-driven approach. You don't know, you have very little intuition about the features because you cannot identify which features are essential or something, but it worked really well. So essentially, we could actually deploy it onto real time, like real world situations. The essential point is that maybe 5 years or 10 years before, if someone would do this sort of work, then people would say that this is basically a useless piece of work because it's all entirely depends on the data, and we don't know what it does with the data and what informations are critical. So, but in the deep learning era, most of these things are like that. But now let's talk about. Now I'll go to the second part. Now, what's the problem with this kind of approach? When we talk about deep learning, what's the problem with it? The major problem about deep learning is that we don't have any kind of intuitive explanation about what does it do inside, what kind of features are important, or what information does it take. So if that is the case, can we do some sort of attacks on it, a simple black box attack? That basically means this is a simple image of a panda, and if I can add some sort of, it looks like salt and pepper noise. Essentially, it's like it's basically white noise. Can we add some noise to it? So this one, like if you see it right now, this is still a panda. So any human would classify it as a panda, but like the classifier basically predicts it as a gibbon. Now how do we do that? I'll come to that. But the classifier basically predicts it as a gibbon. We can do some sort of, so it basically essentially takes the inherent limitations of the deep learning model to orchestrate this kind of black box attacks. We call them as black box attacks because now it gives you a wrong prediction. Now this is quite this particular problem is a critical problem because now on the autonomous driving era, right? So everyone is spending like all the major auto manufacturers are spending billions on the automated driving, and essentially I also do some of those work. So typically, so for example, Tesla basically until now what Tesla does is it basically has cameras that basically capture all these images and then on real time try to find out where a stop sign is or what are all the road signs present, and then do the maneuvers. Of course, they are guided by the maps, but in addition to the maps, you also have all these signs that need to be recognized. So now what you do? What if you post a simple sticker onto the stop sign? A simple holographic sticker. So there are multiple other ways as well. But if this small sticker could basically change the stop sign onto a yield sign, how could we do that? So doing that is pretty simple. Let's suppose the machine learning model, if I know what machine learning model does this stop sign identification, and I know certain limitations that, like if I do a simple modification onto the input of the image, such that to the human eye, it would still look like a stop sign, but to the machine learning model, it would look like a yield sign, or it would look like a speed limit sign. So that way, there could be really, really bad, scenario. So now I tried to do that. First, I'll demonstrate in terms of the old problem that I was describing. So we have all this PMU data that are going to the PDC, and we are doing all these things. Now, what if we take a particular scenario in which someone basically goes onto this local PDC, like local PMUs, and 2 or 3 PMUs data. What they need to do is essentially add some amount of noise. So that can be added just with the help of a simple wireless transmitter. So essentially what it does is you introduce some sort of electromagnetic disturbance onto it. So remotely, and what it would do is just the voltage and current waveforms or this the sensor that basically captures it, it will add some little bit amount of noise. But now this noise is orchestrated. The noise is orchestrated in certain way that it could fool the machine learning based classifier. Now you'd be astonished that actually we could do that. In fact, it happens. So what I did simply was just crafted certain adversarial data. So I basically did it with default. How we do it is, let me explain how we basically do. Let's suppose this functional mapping f of x. X is your input set of data or feature, let's suppose input data, and that gives to some output class y level, right? So now what we do is that add this delta x. This is my noise term, right? The small noise term on different layers of pixels or whatever. So if I add it in certain way that it goes to, it gives rise to a new different class. So now what it happens is that there are points which are near the boundary. And this on this near the boundary, if you basically add a little bit of noise in certain way, craft the noise in certain way that these boundary points basically shift onto the other side of the class. And if it goes to the other side of the class, that's all you are aiming for. And basically, I took a Keras backend, did some training, and then crafted adversarial data just by this optimization function. This is just a simple optimization function to find out this delta x values. Essentially, what happens is this is how the image at the PDC that looks like, and this is what happens to the overall classification. You cannot it's basically you can. A very well-trained model, which basically does it, which looks like a very simple classifier, you can basically reduce its classification accuracy significantly. But in the real world case, what you could do is you could simply do a simple modification and just hope that, let's suppose, you can basically, you can, a completely accurate classifier, you can basically reduce its classification accuracy significantly. Just by modifying all this, these images. Now, how to get rid of it? So one of the key thing to get rid of this kind of deep learning, adversarial deep learning models is again the signal processing helps you. So one of the simplest approaches, what you do is robust training. So in robust training, what you do, you have a set of data, you train the model. Then what you do, you take this data and then add some amount of random noise to it, and do some sort of data augmentation, and then retrain the model again and again. So what you do is, essentially what you do, you craft your adversaries yourself. Take the data, train the model, craft adversaries, train the model again on those adversaries so that the wrong misclassified data is classified again correctly. So that's what we call it as robust training. Like most of the papers don't do it, but I think that this is something which could be like for the budding researchers who want to do something of that sort, you could focus on robust training or some sort of data augmentation techniques that could improve the ML model generally. Then another thing that is very much interesting is called as defensive distillation. Right? In defensive distillation, what you do is you have a teacher model, you train the model, and then what you do is you basically do some sort of knowledge distillation. So now the knowledge distillation is essentially what it does is basically like it's a smaller machine learning model which is extracted out of the bigger machine learning. You do that by parametric extraction, the parameter extraction. So this smaller, the student model will have kind of similar kind of accuracy to that of the teacher model. But what it essentially does in the process of distillation is that it basically tries to make the model more regularized. So in this process of regularization, what we do is we get decision boundaries that are very difficult to to be affected by this black box attacks. The other thing that I didn't focus on is something called as a poisoning attacks. So poisoning attacks are certain other kind of so in the black box attack, you do nothing to the machine learning model. The machine learning model, so the owner basically, let's suppose, so you are not altering any of the Tesla's model, for example. So what you essentially do is you are making some alteration onto the stop signs. So someone goes and some hooligan goes and just pastes some sort of sticker on the stop sign and does that. That's what is black box attacks. If you go with poisoning attacks, what you basically essentially need is you need the model that is deployed on the car or the model that is with the order. So that kind of attack is very difficult, but but that could have adversarial effects. I'm not focusing on that, but with defensive distillation, you could also avoid some of those kind of attacks. Now, like in the deep learning era, where we don't know what the model learns, how it learns, and the exact, the explainability part of it, that becomes a big bottleneck for all these attacks, be it a black box attack or a, like, uh, or a poisoning attack. Don't want to talk about this. So this is another interesting thing. I don't know. In the interest of time, probably I'll discuss other things more. So maybe about this thing I can talk a little bit. I read it's a 2021 paper, so it's a old paper. But this particular paper basically describes an interesting paradigm. What it does is, it basically takes a time series. For instance, let's suppose, now this is going to be funny for everyone. I take a speech recognition model, a very well-trained speech recognition model. I take that complete trained model, and then I use that trained model for my data. My data could be any other time series data. It's not necessarily speech data. It could be any other time series data. And I take that model and does retraining over that. And, so what these guys did was they basically went on to the time series database of, so it's basically, Riverside has a complete database of different kind of 30, 40 different types of time series classification databases. So they took a pre-trained model and they tried to train each of that pre-trained model on each of these, time series data sets. And to their astonishment, they found that they performed much better. So that means a speech processing model, like a speech recognition model that has been trained entirely on the speech data, does well on the other data as well. So that's strange, right? Like, it's kind of like you have trained something to do some purpose. Now you take it and do some little bit of retraining, and it does better than the other ones. That is kind of, it's kind of scary, and it's kind of like, that basically means that, okay, maybe essentially we are extracting some sort of essential feature extraction technique. Maybe like, so think of it as a wavelet transformation used in multiple different domains. But still then we don't know, at least all these transformation based approaches, we knew all these coefficients. But in this case, we don't know much about it. But so it's kind of completely black box things. So this is something, worthwhile to explore. So, okay, now the third, the last part, I would talk a little bit about the federated machine learning part. So the previous thing was adversarial machine learning. The solution approaches were maybe defensive distillation or retraining, or there are other approaches as well. So other approaches means what you could basically do is you can take these weights and have their statistical distribution. Don't want to go over there, but here the last part is federated machine learning part. In the federated machine learning part, if you have smaller machine learning models deployed at say, for example, let's give an example. Take an example of a cell phone. Right? Each one of us owns a cell phone, and when we type on WhatsApp or any messenger per se, so it basically gives us some sort of suggestion, right? The new word suggestion. You could try that. If we are typing in ODS, sometimes it also does ODS suggestions. So essentially, what happens is there is a machine learning model that basically sits in there. It basically learns all your typing habit of what you have been doing, and it basically tries to predict it. But at the same time, you'll see that sometimes you have never used that word, but it actually comes into prediction. So what essentially happens is that every machine learning model which is there in your cell phone basically transmits all their weights in a way to a, let's suppose, a central repository or somewhere through the app, right? Now the app, what it does, it basically combines all those machine learning models, does some sort of fusion, and then makes a model, and it basically sends you back to each of your cell phone. So essentially, it's a kind of crowdsourcing. The crowd, each one of us have certain habits, certain intelligence. It goes back, goes there, it gets fused together, and then it comes back to us again. So what we do is we basically learn our habits at the same time. We also keep on improving things together, and that part we call it as federated machine learning. So it's a federation of stuff. So now I'll give you a quick example that I worked on. So like you know that the energy Internet of Things are getting popularized and a lot of things are going to happen there. So okay. Uh, so in those contexts, I'm just going to talk about some of this, like some of the issues that we face there on the model aggregation front end. So now let's suppose in a EIoT context, let's suppose all these different kind of intelligent devices are connected to to a router, and then it goes on to a energy management system maybe, which can basically automatically control all these differable loads, charging schedules, or the DER generation. But DER, it means distributed energy resources, be it solar or any of those things. And then basically we have all these smart meters together. So my idea here is, so at every home we have all these intelligent devices, and we can have an EMS or a machine learning model that could basically intelligently manage each of these devices. So now what we do is all this, like essentially it goes to the smart meter, right? The smart meter basically perceive them as a aggregated load variation, aggregated voltage or current variations. And all these smart meters, what they do, all these smart meters transmit all this data to a control center. I would say that to the substation. Or like there are different architectures there. The simple thing is smart meter is like a cell phone, which basically you can use either cell phone networks or local wireless networks having 100 or 200 or 700 smart meters in an area communicating with them and all. So there we could use federated machine learning, right? So we could have machine learning doing all this, scheduling of all these devices, and each of these machine learning model is specific to you, and then this models basically transmit all their things to the central repository or the federated server, which basically again sends you back for energy management system. So essentially, what it does is at the home level you do your energy management, and at the aggregate level also you do that. So there are so now coming back to the research challenges that you could basically address there, or the signal processing parts which could do that. A traditional approach is that when we send all these machine learning weights to the repository, am I out of time? So, if you don't mind, how much time do we have? I'll finish the phone. So essentially what we do is, one of the simple approach would be do a secure aggregation. The meaning of secure aggregation is that, what you do is, like, let's suppose you are sending your machine learning weights, right? So even from the cell phone's perspective, let's suppose the machine learning model does some sort of prediction of your chat, but do you want the third party to know what you are typing? It could be a secret message or something. It's a huge privacy violation, right? So the privacy laws, if you look at it, the European laws on privacy right now, GDPR and all, so they have made it very strict. You can't take any of this, like, information and like what we are talking about. But if you look at, like, you can do this experiment. So if you are talking about something, they cannot record anything. They cannot basically, there is no human sitting over there or to find out. So there could be a simple machine learning model which basically takes your data. It essentially doesn't store it. It just sends all these machine learning model weights. So that way, the app providers or the companies are basically saying that we are not doing any kind of privacy, violations. But there have been papers which basically talk about, and it's a significant problem. From the machine learning weights, you can back construct the data. So you cannot do the back reconstruction directly, but there is a possibility that you could still decrypt some of the information from this weights. That's a key problem. So that could become a big privacy violation. So we would not, so that would be like, for example, in your home and all, from your consumption patterns, some adversary could figure out what all devices do you have, or are you there at home, or you are on, like, all these kind of things. Analysis things could be there. And also there is an economic aspect to it. The electrical tariffs are also real-time change. So they get changed based on your consumption. So if someone wants to alter all those things and all, like, play around with you. If your data is directly available to them, they could do that. Like in case of even in case of your cell phone, if the raw data or whatever messaging you are doing could be harmful to you. So one approach to avoid that is basically called a secure aggregation. What you essentially do here is you basically add some sort of noise onto it. I don't want to. So it's kind of it's not source coding as such, but it's simple type of a source coding. What it does is it's as simple as that. I don't want to discuss much. But here with the secure aggregation, the major problem is that you still have to trust the aggregator. The aggregator needs to be trusted with the security, but sometimes you can't do that. So then what you could basically do, now that's it. Here is an interesting thing. Out of all these, all our cell phone users, like 1,000 users, what if there 50% of the, like maybe 20% of the users are corrupt? So their cell phones have been attacked by some virus or something, which basically they could do something by altering your local data, because your local data is now going to the aggregator. So if your local data is, or the local ML model is altered in certain way, then and those ML parameters go to the aggregator, they could actually corrupt the aggregator, and the whole system could crash. So that kind of attack, we call it as model poisoning attacks. So that's also another interesting thing if someone wants to pursue some sort of research on that. Another thing that I thought of was basically using differential privacy for that. So what we did was differential privacy is basically very well known. The whole idea is that what you do, you add some sort of noise similar to the black box attacks, but here you are adding the noise in certain way that it's kind of a coding, you are doing a sort of coding. So essentially what you do is you add little bit of perturbation or little bit of noise onto the data so that the data privacy is preserved. So you can read the data, but that noise doesn't affect anything when it goes onto the decision making process. So don't want to go much depth into it. You can see here this epsilon and delta. These are the, so epsilon is basically the privacy loss parameters, and delta accounts for the small probability with which, the value of epsilon holds. That means that, like the data is not normalized. Right? You have to add the noise based on what's your dynamic range of data and what's the smallest value of epsilon. Don't want to get into mathematics here. So let me quickly go ahead here. So here is something called a differentially private stochastic gradient descent. So we use stochastic gradient descent right now. Like even if we have all these Newtonian algorithms, all these things to train machine learning models, still the most popular approach is stochastic gradient descent, right? So why not embed differential privacy onto stochastic gradient descent? So at the point of time at which you are training the model, what you are essentially doing is you are also adding small amount of noise to it. So that basically does in two ways. The first thing is that it preserves the privacy of the data, because you are making the model of the machine learning model now private. The model parameters private. So that means that someone cannot reconstruct the input data from given the model parameters that are there. It also helps in regularization of the model, and also helps in this is just a quick comparison that I did with differential privacy and using differentially private stochastic gradient descent. I basically used it. It's proposed by someone else. So that it's essentially while you are training your machine learning model, add little bit noise to the data cleverly so that the machine learning parameters become now like appreciated. So now this is something you could explore if you are working on machine learning and you are training it with stochastic gradient. Try training them with differentially private stochastic gradient descent. Check out if the generalization improves. Check out if the regularization improves and things like that. Don't want to here. I just wanted to show a case where if I add differential privacy or stochastic gradient descent with differential privacy, if we do that, then it doesn't have if we keep the epsilon value small, trade-off if we measure it still does well, almost pretty good, performance as we get with differential privacy. Now here, I didn't get into the experimental setup that I used, but it is for a set of smart meter data and it's for energy forecasting. Okay. So now I want to end my talk with the simple note that what are the key stuff that you could work on in machine learning. Let's not get into the black box machine learning models or simply taking a deep learning model and training on our data that we have. That's not something which is going to work on long term. Probably some of these industries, and of course we all are doing that. That's okay. But again, the future lies in explainable AI, right? Explainable artificial intelligence. So what we essentially need to do every time we create a deep neural network, we should also focus on regularization first, and at the same time, we need to know what is the deep neural network learning by itself. One of the way to do that is, let's suppose I take the distribution of the weights in each of these layers and have a quick checkpoint. Okay, this is my distribution of the weights for this particular kind of training. And when I have some sort of poisoning attacks happening, this distribution will change little bit, right? And from that quick change in distribution, we could probably identify, okay, you know what, the model has learned something here in this way, but you have to basically get rid of it. The other thing is called as the saliency maps. Saliency map is something like, it's a very interesting concept. What you do is you basically take the gradient fighting based on the weights, and all this gradient fighting, you basically plot them in terms of images, and you can basically, they essentially looks like a heat map image, and basically you figure out which all weights are critical. For example, you are doing a face recognition, and you know that this part of the weights, this part of the image, or the nose, or the eye, or whatever, they are critical in identifying whether it's a human or it's something else. So if you know all those parts and layer by layer feature propagation, so that helps a lot of that, adds a lot of experimental component to it. So essentially, if some of the, like, if some of you have been searching for research problems to work on or do certain sort of signal processing and machine learning kind of stuff, explainable AI is something which is pretty interesting. So federated learning, explainable AI, and of course, adversarial machine learning. That's all I had today. Tried to make the talk too much, like, kind of jumbled up. Assuming that all of us have a lot of background on that, I just wanted to share my thoughts on it. So it's more like so yeah. So essentially, if I have to make a comment on the programming languages, I don't know, it's a public platform, but essentially Python works really well because you have a lot of libraries, a lot of free libraries. So I'm a MATLAB fan, to be honest. So essentially you could do Python interfacing. So you could use the Python libraries back there in MATLAB, but it's a bit slow. It's a high level language, and Python, MATLAB has Java at the back end. So essentially what happens is that MATLAB is a bit slower in that context. So I would prefer, right now, I would prefer Python. But if there is something MATLAB could do, but it's a proprietary software, if you have access to it, you should do it. But, I think Python is the way to do it. And you can also take R and all, depending on what you want to achieve. And essentially, like, someone told me, it is probably the best, like, biggest organization, in the world revenue wise. So there was, so they basically said that, we don't care what kind of programming languages you know. I think that if you know one programming language, you can know it. Doesn't make any sense.
Whenever you're training this voice signal model, there is a voice signal for other similar type of signals. And we found that that is also performing much better than other type of signals. But still, what about the performance of the system for voice signal? To introduce that, once it is a little bit modified, still it is giving better performance in the voice signals.
Yeah. So here is one thing. So when we talk about generalizability of a particular model, we basically essentially want that whatever kind of noisy environment could be or whatever it might be, the model should perform really well. That's what is one of the inherent assumptions. And then when we talk about adding this perturbation, the whole purpose of adding perturbation is to like either to make the system more robust against this, right? So during the training process itself, we are taking care of it. So we should take care of it in certain ways so that there is no degradation of the performance. That's all. But if there is degradation of the performance, which you have identified correctly that it is most likely going to happen. So still, then what we should basically talk about that model is, no, it's not a 90% accurate model. It's basically 85%. So that 5% that we are talking about, it's not the true accuracy, a true indicator of the performance of the model. So it will be something else. And then probably if we don't train the model on the adversarial data, for example.
Madam, the
Sorry, is there a question?
mic down.
Is there any question? No, I just tried to show that one particular thing you could use it in multiple ways. You add the same noise to make a model adversary resilient. You add the same noise to preserve data privacy. So you could use the same technique in multiple ways. The whole idea was to start from the classical approach that we used to do, we are acquainted with, and what the modern era deep learning stuffs brought to us, and where do they fail, where can we improve, and what's the way. If there are questions, thank you.
Thank you, sir, for the priceless talk. It was indeed an interesting and interactive session. You are our pride, sir, and please keep in touch and visit us soon. Thank you. Our next speaker will join us at 11:30. Let us wait for him.